Okay, so we are doing classification, right? And um, um, we have seen, um, that uh, we have different kind of metrics for classification, right? The 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 main metric that we create is called confusion matrix, and this confusion matrix will give you all the other score, like classification report, accuracy score. Okay, all these are given by your confusion matrix. Now, confusion matrix is a 2 by 2 matrix. Okay, where it will give you the result of your prediction versus actual, right? So how many you predicted and you got right, right? So when you predict something positive and okay, and it's correct, it's true positive. So true and false, the first word indicates whether you got it right or not, right? True means you got it right, false means you did not get it right, right? And then second value talks about what you had predicted, okay? You predicted negative or positive, okay? So if you had predicted negative, okay, that means let's say you, the negative means what you're thinking is not right, in the sense, if it is zero, no, if you take no, right? So no will become your negative. So true negative, false negative. False negative means it was actually yes, okay, and you predicted no. Okay, that's your confusion matrix. And now we will see how to use this. So we are on logistic regression, right? We're still on logistic regression. So we have seen the graph. Okay, now we will do this. We'll do the evaluation model, and with this we'll complete our one algorithm. And then I told you, once we complete it, next it's easy, right? Next it's just about replacing the algorithm with another algorithm, right? Okay, so let's check this out. Okay, um, okay. So how do we create confusion matrix? So I'm going to say CM confusion matrix equal to, okay, um, confusion matrix. Okay, here you pass your Y test, and okay, if you want to create on training, then Y train and Y pred, right? So here our Y pred is on X test, right? And yeah, okay, we are talking about the test, how well the test has been performed, right? So Y pred, okay, and we'll say actual value, which is the Y test value, which we have hidden from the model. This is what we hide from the model, isn't it? This is the actual value, then the predicted value. Same thing we did even in the RMSE calculation. Okay, first you give the actual value, then the predicted value. So Y test and Y pred. So this will create confusion matrix. And if you want to print it down, you can say print confusion matrix is C. Okay. Now, classification report. You want to see the classification report. So I'll say classification R report equal to classification report. And here also you give you want to calculate accuracy. So you say accuracy report or accuracy score, right? So we put AS. And we'll put our AS as. Okay, so this is a keyword for as, right? So that's why, okay, it is giving 2. Okay, so accuracy score equal to this. Now we can print it. So classification report. This is your here slash n is not required. Okay, now let's run this and see the outcome. First time it will take time. Okay. This is your, this we did on white test and white red, right? So this is test data. These are your inaccuracies. Okay. Let's move on. So this is your confusion matrix. Tell me, what do you see from here? Tell me fast. What does this tell you?
Decision will be true positive for 0,
This is true negative, right?
true negative. अच्छा, okay.
This is true negative.
Hmm.
It's true positive. Okay. And yeah, so you're predicting negative. The top you write prediction. So this is your negative, negative. This is false negative. Okay, this is false positive. Okay. Okay. Now, classification reports talks about precision, recall, F1 score, support. Okay. Then you have accuracy. Okay. Accuracy is 85%. So if you calculate this, okay, 61 plus 24 is 85. 85 divided by 100, right? So this is
Yes.
what it is, 85. The accuracy score is 85. Okay. So this is how you can evaluate your classification algorithms. Good so far? Okay. Now we will move to our next algorithm, which is SVM. Okay, support vector machine. Okay. So when you say support vector machine, what does that mean? What did we discuss? Remember? Support vector machine is a process of finding the, now see, we are talking about classification. Okay. not the regression. So here we are finding the biggest possible plane that will separate the two classes. Yes and no, right? So we need to find, okay, a plane that will separate, okay, and the hyperplane is your separation line, okay? So we'll go back here and where are we running the model? We're running the model here. This is our model, isn't it? So I'm going to say here, okay, for now, we'll just put this here. This is your logistic regression. Now we will do our SVC. Okay. So how do you import SVC? You say sklearn dot SVM, right? And import SV. Okay, R for regression, C for classification. Okay. Now you call this. Okay. Now we discussed that SVC has three kernel, right? First kernel is linear. Linear works just like your logistic regression. Okay, so when I put linear, you will not see any difference between logistic regression and SVC. Okay, and everything else remains same. That's all. Okay, everything else remains same. We just have to change the classifier value here. So class is SVC, and this is the value that it takes. Okay. Now if you run it, okay, and going to run P11. Okay, so you see this. This is a straight line. Because we say kernel equal to linear, it give us a straight line. Okay, and value will be more or less, output will be more or less like first regression only. $86. Okay, so there is an improvement of, okay, 0.1%. Now, if you want to change it to different kernel, right? You can change it, can change the kernel, right? So let's say we put kernel as polynomial. Okay, so this is kernel type linear. Okay. Now directly let's go to we have already seen polynomial, right? Let's go to RBF. Okay, so RBF is radial bias function. Okay, and RBF takes two values, right? Your gamma and C. So your gamma, okay, so let me put gamma as 0.01 and C as 1, let's say. Okay, so gamma is 0.01 and C is 1. So you see how the shape will be. And actually, we don't know what is the right gamma for this, right? So we'll have to keep on increasing the gamma. Generally, gamma value will be less than 1 and C value is more than 1. So C value will change from 1 to 100. Gamma, you have to change from 0 to 1. So, 0.01, 0.02. Okay. So we'll have to change like that. It's taking time. So see this? This line got curved. Okay, this is gamma because of the gamma. Now, okay, now if I, okay, okay, change the gamma value to 0.05. And see, when you change it, you have to keep measuring the accuracy score. You need to see which one is giving you higher accuracy. So you see that change? How this curve got changed? As you increase the gamma, this curve is bending, right?
Yes.
Now, I'll go and change the C200. Let's see what happens. Why this is still running? Ah, done, right? So now you see your accuracy score has increased to 91%. So obviously, higher gamma is better, right? And you have to see, I'm doing only one one calculation. You have to do both. You have to do for training and test. That's how you will know whether the answer is in, okay, is it in, um, what do you say? It is in, like, you have to calculate bias and variance. So is it an overfitting area or underfitting area? Because you will only come to know when you do both training and test and see the difference between them, right? So yes, so C is the error, okay? C is the error that is introduced, okay? And gamma dictates the shape of the plane, shape of the plane, okay? So you say this. So accuracy increased to 93%. So you can keep trying, okay? You can try with, okay, what happens if I change it to 1? So as you keep increasing gamma value, it starts getting into overfitting area. You see that? Okay, starts getting into overfitting area. Now if I make gamma as 100, so now see, because this could decrease, right? Now what happens if I give 100? Now you see that? It became islands, right? And accuracy here will be 100% almost, right? No, 71%. It decreased. It's not 100% decreased. Right? So you need to put a for loop and keep increasing gamma and C. So you have to use 2 for loop. In outer for loop, inner for loop, keep changing. Okay. First you fix C and then keep changing gamma. Okay. When you get approximate accurate gamma value, then you fix the gamma value and keep changing C value. Then you will know where exactly is the actual gamma and C value. Okay. All right.
Yes.
Okay. So this is how you will learn, you will do your SVM or support vector classifier, right? Okay. Let's introduce one more concept. Okay. One more concept. This is called as K nearest neighbor method. Okay. So this is your classifier, right? This is because it's class. Kernel, you can read it from here, right? So I just have to say, support vector machine classifier, right? Okay. Next one is called k nearest neighbor. Okay, k nearest neighbor. This is probably easy to understand. Okay, so to perform k nearest neighbor, you will say from sklearn dot neighbors. Okay, neighbors import k uh, k neighbors classifier, right? It also has regressor. You can also do regression. Okay, so k nearest neighbors. Okay, and you say here classifier equal to k nearest neighbor classifier. Okay, and bracket will say n neighbors, number of neighbors. Okay, so one thing is number of neighbors. Second thing is, okay, which metric or which formula you want to use for calculating distance. Okay, so we say Minkowski. Okay, I'll talk about all this. This is also one important. Now, see, most of the algorithms, okay, we like in regression also you saw that we find the distance between point and the regression line, right? That's how we calculate the error. So we need to know how to calculate the distance. Now, when you look at Ola, Uber app, right, they will tell you that car is so many kilometers away from you. How does they calculate the error? So there are three main methods of calculating distance, not error, distance. So how do you calculate the distance, right? So one of the method is Minkowski, and I'll talk about other methods. Okay, we have Manhattan distance method and things like that. We'll get into that. So first, let's understand how k nearest neighbor classifier works, right? Okay, so you give the training data, right? You give the training data. It will plot the data on the plane, right? When a new point comes, when you're testing it, when you're predicting it, okay, so when you predict, a new point comes and it looks at number of neighbors that you have given, okay, so it will look at the 5 nearest neighbors. Which are the 5 nearest neighbors? And then it will see those 5 belongs to which classes, okay. So if 3 belongs to yes and 2 says no, then it will give you yes, because majority value says yes. Okay, and that's why the distance that we give here, or number of neighbors that we give here, should be odd number. Because if you give 4, it is possible that 2 can be yes and 2 can be no. Okay, so that's why we give 4. So okay, and then what we also do is then next question comes. Okay, what is um your best k value, right? What is your best k value, right? Should it be 1? Actually, odd number, right? Not even number, because it's possible that it can happen that 2 and 2 or equal number of values can fall in both the classes. So even numbers are ruled out. Odd numbers, it can be 1, 5, 1, 3, 5, 7, 9, 11. What should be the best number of k values, right? So okay, so what value should we give here, okay, in k? Did you understand what k indicates? Okay, so let's say if you want to know, okay, generally see, um, bad example, but it'll be easy to understand. Let's say when you go to heart of a state, any state, okay, it's easy to know the people in that state will speak the language. What is the official language of that state, right? Okay, okay, but let's say you are at border, right, and there's a new person. You want to predict which language that person speaks. Okay, it's a border state, so you don't know which language this person will be speaking. So what do? You look at the neighbors. Who are the neighbors? Okay, you look at the 10 neighbors. But do you look at 10 neighbors? No, you can't look at 10 neighbors, right? You have to look at 9 neighbors or 11 neighbors, right? And see what language they speak, because those are training data. You already know them. Okay, supervised algorithm. So you know the training data. The neighbors what language they speak. Okay, and if majority of the people speak Okay, let's say if you are at Karnataka and Telangana border. If majority people speak Telugu, then this fellow will also be a Telugu guy. If majority people speaks Kannada, then this guy will also be a Kannada guy, right? So if I have to show you on the graph, let me open Paint. So let's say you have XY, right? Age and salary or whatever, right? And let's say you have yes value represented using this color. These are yes, let's say. And let's say these are no. These are no. Now, if a new value comes here, this value, okay, we need to predict with this customer will buy your product or not, right? These values are training data. So you know these are customers who have bought the product and these are customers who have not bought the product. So what will this value be? Okay, will this customer buy your product or not? Right? So you look at the neighbors. How many neighbors are there? So if I put 5, okay, now you see if I have to find the distance, okay, so I have 1, 2, 3, 4, and 5. Let's say these are 5 nearest neighbors, let's say. So you see, majority of the values says no. That means person will not buy, right? So this will be predicted as orange. Okay, no. Okay, this is how your nearest neighbor works. Very simple technique, isn't it? Okay, but very powerful. But here, okay, we need to know the distance because see here you have to measure the distance, right? There are 3 ways to measure distance. Okay, one is Minkowski, obviously. Okay, second one is called Manhattan distance. Okay, third one is your Hamming distance. Minkowski is simple. The Euclidean distance. That means you do the square root of distance between them, right? You say x1 minus x2 whole square plus y1 minus y2 whole square and square root. This is what we learned in our school days. So that is called Minkowski method. Okay. Your Hamming distance is it looks at the vector. Okay, so this also tells you the direction. Okay, look, Hamming distance will also have the direction. You look at the it's the distance between the vectors. Okay, and then Manhattan distance. Okay, is also looks at the elevation. Okay, elevation. Okay, here you have xy value and also the height elevation. Okay, and generally your Ola and Uber, okay, they use Manhattan distance to measure the distance between you and the driver. Okay, so that is okay, I have it here. Okay, just give me a second. I'll show you the details. Okay, I'm opening my notes here. Just give me a second. Must be in this chapter. have it. Yeah. It's bivariate regression. Multivariate, bivariate, okay. Types of distances, yeah, here. Okay. So measuring distances. Okay. So when you talk about measuring distances, okay. So you know, so where is the okay? Now see, when you perform algorithms, right? There are some algorithms where distance is important, right? Majority of the algorithms, distance is important. We talk about regression line, and you want to calculate the error between them, distance. K, K nearest neighbor, distance. Logistic regression, we don't measure the distance, right? Logistic regression, we don't measure the distance, right? Distance is not important, but in K nearest neighbor regression, okay, you're you have to measure the distance, okay. So there are actually four methods, okay. One is your having distance, okay. So here you see K nearest neighbor we'll use. Then you have K means clustering. Here also we use types of distance. So that's a clustering algorithm, okay. After classification, we'll do clustering. There also we'll see how to use K-means. So you have Hamming distance, Euclidean distance, Manhattan distance, and Minkowski distance. So having distance calculates distance between two binary vectors. Okay. So let's say if this is one vector and it can be any dimensional. Okay. Vector can be any dimensional, isn't it? So it can measure distance in 3 dimension also. So here you see, here you have red, let's say 1, 0, 0, and green 1, 0, 0, 1, 0. Okay. The distance between red and green could be calculated as sum or the average number of bit difference between the two bit string, right? So that's what I said. 1 minus 0 plus 0 minus 1. So 1 minus 0 whole square plus 0 minus 1 whole square. And then you do the root, right? I mean, if you have 3, then you do the x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square and do the square root, right? Okay. So, okay. No. That is Euclidean distance. Sorry. Here, okay, so here we know there's no square here. You do the absolute value here. So sum for, so it is x1 minus x2. Okay, let me put it here. Your Hamming distance is x1 minus x2. Okay, plus, and so you calculate here it says you calculate absolute value. Okay, so it is absolute value, right? Then you have y1 minus y2, right? Plus, okay, so on, right? So if you have 3, it becomes 3 and divided by, okay, so this entire thing will be divided by number of points. In 2-dimensional, you'll have 2, 3-dimensional, you have 3. So if it is just x, y, it will be 2. If you have x, y, z, you have 3, okay? You can divide by n-dimensional divide by n. So this is how, okay, there's no square here, okay? Now Euclidean distance is where you do the square and do the square root, okay? So, because see, because when you minus x1 and x2, you get negative numbers also sometimes, right? So how do you make negative numbers positive? One way is do the absolute value, right? Just like if you remember in calculation, we did absolute error. Okay. Okay. So in absolute error, we just took the absolute value. Okay. We ignore the negative values. Here too, we ignore the negative values. Okay. Here, instead of ignoring negative values, you do the square. So it will be x1 minus x2 whole square. Okay. Similarly, you will do y1 minus y2 whole square. And then you will do the square root. And you do the square root of the values. Okay. Okay. And there is no average value here. There is no n here. Just the square root. This is what we have done before, right? In our school. Okay. So this is Euclidean distance. And you can do the square root of the square. Okay. So this is your calculation of Euclidean distance. Then Manhattan distance. Okay. It is sum of, okay, sum of V1 minus V2, right? There is no square root, right? And absolute distance you take of the entire value, not each value. Okay. So here what we're doing, here we're taking absolute difference of each value, right? Here, you see absolute value is outside the bracket, right? That means you take the absolute value outside this. Okay. So this is your Hamming distance formula. The Manhattan distance formula. Minkowski, okay, okay, so add them absolute value. But here you see, after doing the absolute value of x1 minus x2, you have to raise it to the power of p. Okay, so see, including distance, you do square and square root. Here it says, okay, Minkowski, that you look at the number of values. So here it will be power of n. Okay, power of n and nth root, right? So it is power of n and then you do the nth root. That's your Minkowski distance. So when you're calculating this, you can put Minkowski, you can put Euclidean. Okay, whichever method you give, that method will be used to find the distance between the input point and the training points. Okay. So, okay, so I'll put this link so that you can actually refer them when you are there. So I'll say here, refer types of distances. Okay, so you'll be able to read that. Okay, so there are different formula of calculation of distance. That's what it says. Okay, so I'm saying use Minkowski or use Euclidean. You can mention it here. Okay. Right? Okay. Now that is about metric, right? Distance. Now, how many neighbors should we select? What do you say? How do we select the neighbors? Any idea? See, in SVM, okay, or SVC, I should say, in SVC, okay, our objective was to find the best gamma and C value, correct? Gamma value is more important. C, of course, C is also important. So our objective was to find the best value for gamma and C to know, how our model will be the best possible model. Yes. In neighbors, okay, in K nearest neighbor, K and C, okay, K nearest neighbor classifier, our objective is to find number of neighbors. Should I take 1, 3, 5, 7? What should you do? Again, you'll have to run in a loop, and loop will take value as 1, 3. I mean, you should generate odd numbers. Okay. And you have to compare your validation error and your training error, right? So your validation error will start decreasing to a point and then it starts increasing, right? That's what we saw, right? What did we discuss about bias and variance? Okay. So your training error will generally keep on decreasing. Your validation error will decrease to a point and then increase, right? So this is your best K value. So you have to run your algorithm with 1 to maybe 100, 200 values, and you see that validation error. That validation error will start decreasing. That means your accuracy will increase. Your accuracy will increase to a point. Okay, so let's say you start with 60% accuracy. It goes on till 85%. And after 85%, it starts again increasing, becomes 83%, and it becomes 50%, right? So you know that this is the best number of K. So if it like 1, 3, 5, 7, if it is 9, then K9 is the best number of neighbors that we need to select for that particular data set. With me, everyone? So we'll stop here for today. Okay, so today we have covered how many algorithms?
Yes.
How many? We have covered SVC,
Mm.
then we have covered K nearest neighbor. Yes or no?
Yes.
So this is K nearest neighbor. This is your SVC, right? And we saw the evaluation of all these algorithms. So if you see here, K nearest neighbor is giving us 70% accuracy, 71% accuracy. What if I make it 9? Then what happens? So this is, okay, now you see, it became 93% accuracy, isn't it?
Yes.
So here, definitely your 9 looks better than 5. Okay. So this is how you evaluate your models. All right. So we'll stop
Yes.
here and, we will continue from here tomorrow.
Okay.